In the last class, we have seen theoretical aspect of fractional flow equation, and we have also covered the derivation part. So if I conclude the last video, we can see that fractional flow defines relative movement of this specific fluid at each and every point in our reservoir. Fractional flow depends upon several parameters. Relative permeability is one of them. Relative permeability depends upon saturation. So we can say that fractional flow equation ultimately depends upon saturation, although we do not define that specific relationship in our equation. So if we make a plot of FW versus SW, which we usually do in the laboratory experiments. So when we make a plot of FW versus SW, we basically define a function telling you different values of FW at each and every saturation. So this is some sort of data which we have to take. Now once you have defined the fractional flow equation, what is the next term which you need to know? You need to know saturation at each and every point in your reservoir. So in order to define this saturation profile at each and every point in our reservoir, in order to define this fractional flow, we will make use of Frontal advanced equation. So Frontal advanced equation is basically study of saturation profile. So Frontal advanced equation is second part of frontal displacement theory, and this equation is derived with the help of volumetric balance. So before starting the derivation, we'll see what are the assumptions. First assumption is that there is an immiscible displacement, and immiscible displacement is a very basic term that the water which you are injecting in this reservoir block is displacing oil, and water is not getting reacted or water is not getting dissolved in your oil. So there is a pure mechanical displacement which we also term as piston-like displacement. Now the second major assumption is that we neglect capillary forces and gravitational forces. So even though we know that this is your reservoir block is a porous medium, and capillary forces is one of the most crucial parameter in defining the flow of fluid. So capillary pressure depends upon the saturation, and saturation which depends upon the distance. So we are basically neglecting this whole scenario, and we have seen this in the case of derivation of fractional flow equation. In the end, we neglect the capillary pressure term, saying that its effect is not very large. So we will use the same equation which has neglected the capillary forces to define Frontal advanced equation. So let us start with volumetric balance. Now this is your reservoir, and there is a linear flow. It has some phi porosity. A is the area of cross section, and dx is the thickness of this element. So this element is basically a small thin cross section of this reservoir slab in which your water is contacting with your oil. So it is a sort of point of contact in your reservoir, and once we make our volumetric balance, so volumetric balance basically says that volume which is getting inside this element minus volume which is coming out of this element is equal to the volume staying inside or remaining in that element. कुछ जा रहा है, कुछ बाहर आ रहा है, but there is some difference between the inflow and outflow, and that difference is defined by remaining volume. So we will use fractional flow equation as we will only consider water in this case. According to fractional flow equation, this is what we can use. This will be basically your flow rate of water. So this is your flow rate of water which is multiplied with a very small amount of time, because it is a very small part of the reservoir. minus, now since it is a very small part of reservoir, there will be a very minute change in fractional flow rate. And the remaining volume will be defined by, this will be the bulk volume of this specific region, but since this media is porous, it will have some porosity, and the volume has, sorry, the water has just entered this specific element, so the saturation will be very small. So this is the equation, and if we rearrange this equation, if we rearrange our equation, this is what we will obtain. So these values are actually variable, they change with time, they change with position, that's why they're defined for one specific saturation, as this element will be valid for one specific saturation value. Now this is basically your slope in FW versus SW graph. We will see different aspect of this graph later. And dx by dt, which can also be written as velocity. So not only we are defining the position or time of saturation, but we are basically obtaining the velocity. Now if we try to visualize this equation, this is our reservoir, although it does not look like a reservoir. Suppose it is our reservoir, and we divide our reservoir into smaller blocks. Now on injection, water saturation will be different in this region, water saturation will be different in this region. Therefore we can say that each and every block will have some specific saturation. And let us say this specific block has SW1 saturation, and after some time, after more injection, this specific saturation will move further ahead to this point, which was earlier having lesser saturation value. So it will cover some distance in time t. Therefore this specific saturation value will have some velocity. So this movement of saturation from one point to another point of the same reservoir is defined by this equation. And also not just the velocity, but we are ultimately obtaining the position of any saturation at time t. So interchangeably what we can do, that you can ask the position given that saturation has traveled time t, or you can ask that how much time this saturation will take to cover distance x. So this is what we obtain with the help of these equations. And once you take out dt and integrate both the side, t will add up here, and basically they will give volume. So Q into T can also be written as volume. Now QT can be replaced by IW or injection rate, because injection is the only thing which is causing all of this movement. So we can replace QT by IW, and if we replace QT by IW into T will basically give you cumulative volume which is injected. So once you are able to calculate the amount of water you have cumulative injected into your reservoir, you will be able to calculate the distance traveled by different saturations. And this equation is in consistent units. That is, if let us say your x is in feet, or let us take another unit, if it is in meter, then this will be in meter cube, area will be in meter square, and these will have no units. They will have, F will have unit, but it is a ratio, so that will not make sense. And if you replace it by QT into time, then it will be given in meter cube per second, time will be in second. It can be in days also. So depending upon different units, if they are consistent on both the side, if the final of all the cross cutting is the same on left hand side as well as on the right hand side, then this equation can be used. So I would recommend you to use this equation, or to remember this equation. And if you want to convert it into the field units, then basically you can consider x in feet, so I will be in feet cube per day, time will be in days, divided by area which is in feet square, and we are not concerned with the rest of the part for deriving the units. Now if you try to convert it in BBLs per day, then you can simply make a minor change by multiplying it with 5.615. So by multiplying this thing by 5.615, and your Q will be in BBLs per day, you are basically getting the field unit form. Alright, so let us talk about the slope part, dFW by dSW. So we have seen earlier that with the help of laboratory experiments, we are able to define this curve where a fractional flow values are plotted against each and every saturation. Now once you are able to obtain the saturation at each and every point in your reservoir, you will be able to calculate FW at that specific point. So let us talk about the derivative dFW by dSW, which is one of the variable given in the equation. So if we talk about the derivative of this curve, we can see that till this point the rate in increase is also increasing, but beyond this point the rate of increase is decreasing. Hence this is the derivative curve which we will get. And what we can see that at two different saturations, same value of derivative can exist. So once you put the slope in this one particular equation, what you will notice that all the values are same for one specific time. At two different saturations you are getting same slope value. So basically at one position in your reservoir there are two different saturations, and that is impossible. So this was one sort of interpretation And once more work was done on this one specific equation, the assumption that we are neglecting capillary pressure or capillary forces was taken out. So this curve is again defined by taking capillary force term into our account. So if we see the capillary term, your Fw is given by this equation. So Fw is given by this equation, and while defining this specific curve of Fw versus Sw, we neglect this term. Now we add this term again and see how actually it changes the whole interpretation process. So capillary pressure is changing with x, and let me draw one more diagram. So in order to visualize this change, we'll consider this as our reservoir. This is your injection well, this is your producer part, and this is how your x is varying. Now what it is saying that capillary pressure is changing with x. And how is that possible? Capillary pressure is function of saturation, which we have seen in the reservoir classes, and saturation will be the function of x because this is your injection point and this is your producer point. So for a very long period of time, this will remain a region of high water saturation. सीधी सी बात है, यहाँ पे पानी ज़्यादा भर रहा है तो saturation यहाँ पे ज़्यादा होगा. So the saturation, on an average, we can say that saturation is decreasing in this direction. This is the region of higher saturation, and since the water is getting reduced, the saturation will also get reduced. We are talking about water saturation only. So since the saturation is changing with distance, capillary pressure will also change with saturation. And since this is a region of high saturation, high water saturation, capillary pressure will be less. This is a region of low saturation, low water saturation, then capillary pressure will be higher. We have seen that Pc is the difference of PO minus PW. So this is the major change which is happening on neglecting this one term. So once we add the effect of this term, the nature of graph of Fw versus Fw will change. So now they added the effect of capillary pressure and they changed the type of curve. So this is the type of curve which we are getting on adding the effect of capillary pressure, and this red line denotes the earlier curve. So in this case, the rate of change is constant. Now if we define the derivative curve, what you can see, from this point to this point there is a straight line, therefore the rate of change will be constant, and from this point there is a decrease in the rate of increase. So this will follow the same path which it was following earlier. So another interpretation was made by one different scientist, and what he said that from this saturation SWC, from where the water starts flowing till this saturation, which is called as SWF, the velocity will remain same. Not only the velocity, but the variation of x will also remain same, because given that all these conditions remain constant, such as QT, A, porosity, area, these will actually remain constant. The only thing which changes is slope. So another interpretation was made in such a way. What was the earlier interpretation? That one specific block of reservoir cannot have two different saturations. But now this graph is seen in a different way this time. What they are saying now is that from SWC to SWF, all those saturation blocks will travel same distance in any given time t, and beyond this point the distance, or basically the speed, will change. So if you try to visualize that with the help of simple diagram, what we can see is that there is one injector well and there is one producer well. This is the rough sketch of injection, that this is your water. This will be a region of high saturation, this will be region of low saturation. Let us say this is the point where the saturation of water is least, and this is your SWF. So this whole block will travel at same speed, and beyond this point the movement of saturation block from one part of the reservoir to another point of the reservoir will be different. The velocity of each and every saturation is different in this case. So this whole block will move together while this block will move far apart, because there is a relative displacement between the saturation from SWF to 1 minus SOR. Therefore, SWC to SWF, this block is called as stabilized zone, because there is no separation in this region, everything is traveling together. ये आगे वाला भी आगे बढ़ रहा है तो ज़्यादा saturation वाला block भी पीछे पीछे आगे बढ़ेगा. But unlike this, saturation SWF to 1 minus SWR, this specific block will continue to expand because they have a relative displacement, and hence they will be called as unstabilized zone. And this point of division is called as shock front. Alright, so we have defined this stabilized zone and unstabilized zone, and if I try to define it in more simpler terms, then I can say that higher saturation water block will travel at different speed. Or if we take this thing numerically, then we can say that from SWC to SWF, everyone will take t amount of time to travel one specific distance x. But from SWF to 1 minus SOR, depending upon their saturation, they will take different times. One will take T1, one will take T2, one will take T3, and so on. And as the saturation increases, the time taken by the block, the saturation block, to move ahead will also increase. So this higher saturation block will get slowly, will move ahead slowly, but this specific zone will move at a fast rate, and it will move with same speed, same rate. So this is it about the theoretical part about the frontal advance equation. In the next video, we will see the procedure of how to actually use this equation and how to make better result, how to gain better outcomes using this frontal advance equation.